So today we're doing a review for the midterm. So the midterm's on Monday. It'll have a similar structure to the first midterm. Please remember to bring a calculator. It'll be a mix of multiple choice, objectives and diagrams, and then some calculations at the end. I posted yesterday a list of all of the lectures that are covered in the midterm. So I think it starts around lecture 11. And then goes up to the end of tsunamis. And so it starts right after hurricanes, so when we start talking about measuring ocean velocities and things like that. I'm working on a list of the sort of most important diagrams that you can sort of focus some special attention on. Not to say that the review lecture or the list of diagrams or whatever contains every single thing that'll be on the material, on the exam covers all the material. But in general, that's a very good starting point. Okay, so we started off this section of the course talking about the sort of really oceanographic aspects, measuring ocean surface currents. We discussed a number of methods that we can use to measure ocean currents. And one of them that's shown here is a drifter or a float. And so this is something that you put in the ocean and it moves with the ocean currents and then sends back data so you can track where its position is, and then through the position you can get the rate of change and get the velocity from that. And methods like that, where you have a float and the float drifts with the ocean currents, those are called Lagrangian. So Lagrangian means the instrument itself is moving and you're sampling the velocity kind of across space. The alternative to that is called Eulerian, which is, for example, a fixed current meter. So the current meter is shown here on the side. So basically it has a propeller on it, and as the current goes by the propeller, causes it to rotate, and then based on the rotation rate, we can measure the current. So two types of, two broad categories of measuring currents: Lagrangian methods where something moves, and Eulerian methods where it's fixed in space. Another sort of famous, funny example of Lagrangian methods is when objects are dropped into the ocean by accident, and so these cargo containers, they fall off all the time, and stuff falls out of them and floats away, and so just by tracking the motion, in this case it was sneakers, you can look where the sneakers go and infer something about the currents. Another method is to use the Doppler effect. So the Doppler effect basically is that phenomenon where when you hear a siren like an ambulance or a police car coming towards you, the pitch starts to get higher, and then when it's going away, the pitch gets lower. And that's because the wavelength of waves is shifted when the thing that's either emitting or reflecting them is moving. And so what the Doppler, what the oceanographic instrument is called is the acoustic Doppler current profiler, or ADCP. And what it does is it emits sound waves, so that's the acoustic part, and then it reflects off of stuff in the water column. So this can be like fish or small organisms. When the waves reflect back, if the object is moving away, the wavelength gets stretched out, the frequency drops. And if the object is moving towards the source, the emitter, the wavelength gets smushed together, and the wavelength gets higher, and the frequency gets higher. And so by measuring back at the emitter, the shift of the wavelength of the sound waves, we can infer the velocity of the moving object, and then infer the velocity of the water that's embedded in. We can also use satellite measurements. This is some data from a satellite altimeter. So this is radar altimetry. So this uses radar waves, which are kind of lightweight. And these waves, they emit it from a satellite, bounce off the sea surface, and then return to the satellite. You can use the travel time to measure the height of the sea surface. And then we get the high and low. We get what's called the topography of the sea surface. Regions where the sea surface is high or regions where the sea surface is low. And then those can be used together with the concept of geostrophic balance to determine the velocity of the water from space. Another major program is called Argo, and these are drifters again. So these are subsurface drifters in this case, so they're different than the surface floats. So they go to a predetermined depth, and then they go with the current at that depth. And you can see that since the beginning of the Argo program, which was a few decades ago, many thousands of floats have been deployed all over the ocean. And what these Argo floats do is that they coast at a certain depth, and on occasion they return to the surface and then send their data to a ship or to a mound-based observational center. So there's lots of floats all over the world, and Argo is a key way that we get subsurface information, like things about what's happening in the thermocline, what's happening with stratification below the surface, and things like that. Another way to measure subsurface currents is to look at what are called tracers. So tracers are any particle or any substance that's sort of dissolved in the water and then it moves with the flow of the water. So for example, some famous examples are pollutants that we emit. So things like chlorofluorocarbons, CFCs, which are associated with the ozone hole. If you know that little bit of famous history, the Nobel Prize was given out for that. And these pollutants or whatever, there can also be stuff from nuclear tests, like certain isotopes, tritium, and these things get dissolved into the ocean at the surface, and they're emitted they're injected just at the surface, but then we detect them at depth, and if we make measurements separated in time, so this, for example, is a measurement from the early 70s, and this is the early 80s, we can see that the distribution of these pollutants has changed in the ocean, and that's because the deep, slow currents have moved those pollutants from the surface down to depth and then outward back into the basin. And so this is the North Atlantic, and so we can see that there's this sinking happening, bringing the pollutants from the surface down to depth. That's North Atlantic deep water formation or deep convection. We'll come back to that. A big topic that we spent quite a bit of time on is the gyres, the subtropical gyres. And so these are these circular circulations that are in all the ocean basins. In the northern hemisphere, they rotate clockwise. In the southern hemisphere, they rotate counterclockwise. And they're in all ocean basins. So we have a North Atlantic subtropical gyre, South Atlantic, North Pacific, South Pacific, and then Indian. So we have 5 of those subtropical gyres. And they're bounded by currents on all 4 sides. So we have a western boundary current, northern boundary current, eastern boundary, and southern boundary. And the physics of these things, you can sort of remember that essentially they're pushed by the wind, and then they turn when they hit land, and the way that they turn comes from the Coriolis force. That's a little bit of an oversimplification for sure, but that's a way you get, at least it's a way to remember the answer. So let's look at the North Atlantic subtropical gyre. So down in the equatorial part, as the subtropics actually just a bit north of the equator, we have the trade winds blowing from east to west. And those trade winds drive the southern branch of the flow to flow from the east to the west. Then it hits the land, North America. Then because the Coriolis force deflects you to the right, you turn right. And we have the Gulf Stream coming up the western side. When it gets to the top, it turns right again because of, again, Coriolis force direction. The North Atlantic current runs across this way. Also, this is blown by the westerlies. We hit land, turn to the right, and then travel down here. This is the Canary current, is the eastern boundary current, and that creates the cycle. And you can think about how that operates in the southern hemisphere. As this thing goes around, you can see it's always turning left. And that's associated again with the Coriolis force. So being able to sort of reconstruct these gyres based on that physical argument, this is a pretty important diagram I would definitely pay attention to. And also, so the names of, so there's all sorts of names for the currents in these gyres. The only ones that I want you to care about are the ones in the North Atlantic. You should remember Gulf Stream, North Atlantic current, North Equatorial current, and the Canary current. Okay. So this is just a figure showing the diagram of all of the names across all the world. You don't need to know those, but knowing that there's 5 gyres and knowing the direction of rotation in the 2 hemispheres, that's important. Okay, Ekman. So there's several topics related to Ekman, and these all have to do with when there's wind blowing over the surface of the ocean. So the original observation was that they were on this boat, oceanographic research vessel, and they were looking at ice and the movement of the ice. And what they found was, rather than the ice drifting directly in the direction of the wind, which is what everybody would expect, they actually drift at an angle. So they drift somewhat to the right of the direction of the wind. And that's again attributed to the Coriolis force. And the history is that this guy Nansen was the sort of the main scientist, and he put this guy Ekman on the problem, and then it's now named after Ekman. Oh, and I actually don't have this in the slides for some reason, but the key idea here, I'll just say verbally, is that when you have the wind blowing over the surface of the water, what happens is you have wind blowing this way, and if you look at the velocity at different levels, as you go down, it rotates and it gets weaker. So there's kind of a spiral pattern. That's called the Ekman spiral. And then also, if the wind is blowing this way, in the northern hemisphere, there's also an Ekman transport. There's an arrow that goes to the right of the wind. So the Ekman transport is the average over the Ekman spiral And it says that basically, if you have wind blowing over the surface of the surface of the ocean, let's say the wind's blowing north, then the overall movement of the water underneath that wind is going to be to the right of north, which would be to the east. And so it blows to, so the overall transport of the surface waters is to the right of the wind in the northern hemisphere and directly to the left of the wind in the southern hemisphere. And that's called the Ekman transport. So that Ekman transport plays a key role in driving upwelling and downwelling. So when we talk about upwelling and downwelling, we mean the vertical motions of the ocean water. And if you think about how Ekman transport operates near a boundary, you get very interesting and cool effect that's very important for biology. So this example is like you can think about the coast of California. So this is the west coast of a landmass in the northern hemisphere. And let's imagine that the wind blows from the north to the south here. So the Ekman transport at the surface level will be to the right, which would be offshore in this case. And so it's pulling water away from the coast, and that water has to be replaced by upwelling water from below. And so whenever you have this configuration where the wind is blowing along the coast in this direction so that the Ekman transport is offshore at the surface, that always causes it causes coastal upwelling. And this upwelling brings lots of nutrients and stuff to the surface, and so biology that are in that photic zone that are near the surface, because that's where the light is, when you bring the nutrients up from below, that can explode the productivity. So if you look at ocean chlorophyll, for example, you often see a lot of enhancement of ocean chlorophyll along the coasts, and particularly in this situation where the wind has this orientation. So if the wind has the opposite orientation, so imagine the same setup, but now the wind's blowing from the south, so now everything gets reversed. So the Ekman transport is now to the right of the wind, which is onshore. That sort of piles water up onto the shore, and that water sinks and then it gets recycled down below. And so you actually have sinking or downwelling near the shore. And that means that the biological productivity is suppressed because there's no nutrients coming up to the surface. And so you get very little chlorophyll in the water there. Up in the upper left, this is the other example of upwelling called equatorial upwelling. And so this happens because the trade winds, if you imagine this is the equator, the trade winds here blow from east to west, and so the winds are blowing in that direction. So north of the equator, the Ekman transport is to the right of the wind, which is to the north. So that's why we have these arrows that are going to the north there. And south of the equator, the Ekman transport reverses direction. So now it's to the left of the wind. So you still have that same trade wind blowing from east to west rather. And so the the Ekman transport is now to the south. And so the water kind of spreads out, driven just by Ekman, at the equator, and then water has to be resupplied from below, and so we get equatorial upwelling. And so this is a picture of global ocean chlorophyll. And you can see that lots of these coastal areas, here's California, lots of productivity near California, like in our coastal upwelling example, and then along the equator too, we get this band of green all through the equatorial regions, and that's associated with equatorial upwelling. Okay. So another exercise we did is we just went through all the basins and we were looking at what were the main circulation patterns. And we started off with the Southern Ocean. There are really two main things that know about the Southern Ocean, the two main currents. One is called the Antarctic Circumpolar Current, and that's driven by the mid-latitude westerlies in the Southern Ocean. And that goes from west to east all around Antarctica. So it's the main purple shaded region here. It's the dominant current, most energetic current on Earth, I think by far. It circulates all around Antarctica, and there's no continents to block it. It goes through this narrow region called the Drake Passage, which circulates around and around. And then inside that, closer to the continent, the winds reverse because we have the polar easterlies, and then the current reverses as well and circulates from east to west, and that's called the east wind drift. So just know in the Southern Ocean that there's two currents. The ACC, Antarctic Circumpolar Current, is on the outside, driven by mid-latitude westerlies, and on the inside, we've got the east wind drift, which goes in the opposite direction. We also looked at the Atlantic, and in the Atlantic, the main, most dominant feature is the Gulf Stream. So the Gulf Stream is a warm current that comes up through the Gulf of Mexico, up the eastern seaboard, and then flows up, and then detaches and flows out into the open North Atlantic Ocean. A key phenomenon that we talked about is these Gulf Stream eddies that come off the Gulf Stream. And so how this works is the Gulf Stream has these sinuous bends in it. That's because it's turbulent. So the Gulf Stream is kind of intrinsically unstable. There's lots and lots of interesting physics to study about that, but it's a bit more advanced. You would see that in the third year or the fourth year course. But this Gulf Stream has all these wiggles that develop spontaneously. And then sometimes those wiggles, they break off and they pinch off and become closed recirculating eddies. And what happens is the ones that are, so generally, down here we have warm water because it's more equatorward, and up here, that's Newfoundland, so we have colder water up here. So when you have an eddy that's on the southern side, it came from the north side. So eddies that are on the southern side, what happened was there was a bend, and like this little bit of cold water here like breaks off and becomes an eddy here. And so that tells you two things. It tells you, one, that the eddies are cold relative to the surrounding waters, and it also tells you the sense of their spin, because the eddies here are spinning counterclockwise, and that's because of the way the curvature of the Gulf Stream was before they pinched off. And vice versa, on the northern side, any eddies, they came from the southern side. They pinched off the southern side, and so these would be warm core eddies. They're warmer than surrounding water, and also they rotate clockwise. And so you might be asked to tie together, for example, if you look at an eddy on this side, is it cold or warm, and what way should it rotate? Those are and you can basically connect it to just imagine the scenario of the S-shaped sinuous Gulf Stream, and then imagine it pinching off, and just draw the arrows of the flow, and you'll get the correct sense of direction. Okay. The same principle applies in the Gulf of Mexico, where we have what's called the loop current. So the loop current is just the beginning of the Gulf Stream. So the Gulf Stream goes up the eastern seaboard, but it loops into the Gulf of Mexico first, and there it's called the loop current. The same thing happens. The loop current has sinuous S shapes and wiggles in it. Those wiggles break off and become circulating vortices, and they can either be warm core or cold core, and they can either be clockwise rotating or counterclockwise rotating. And these eddies we studied actually in a lot of detail because we looked at them quantitatively using satellite data. And what we observed is that the rotating eddies in the Gulf of Mexico, they're associated with sea surface height anomalies. And so this one here is clockwise rotating, and that's a sea surface high. This one here is counterclockwise rotating, and that's a sea surface low. So the blue colors mean low sea surface height. It's not temperature. This means the sea surface height is a few centimeters, 10 centimeters lower than sort of average. And here we have 10 or 15 centimeters higher. And we did a detailed analysis of the forces involved. We looked at this slab of water in between these two eddies. And what we found was that the dome and the bowl of water that are associated with this red and blue region give rise to pressure forces. And then in geostrophic balance, those pressure forces are canceled by, or they're balanced by Coriolis forces. Coriolis force requires a velocity, and then so you can estimate the flow velocity in between here. And what we found was that our calculation matched up. We did some calculation. It was almost the whole class. And our calculation gave us a velocity which was quite consistent with what we found from the data. And so knowing this example, much like in the first midterm, you could be asked to do some geostrophic balance kind of calculation. Would be one. I would say the two main kind of calculations that you might be asked are something related to geostrophic balance and something related to waves and dispersion relation. Those were the two most mathematical parts that we covered. Okay, continuing, going basin by basin. In the Indian Ocean, the main thing was the monsoon. So the monsoon, basically, if you understood the sea breeze from the first part of the course, the monsoon is just a continental scale sea breeze. So the idea is we're looking at the sort of Indian subcontinent and Southeast Asia here, which is where the monsoon is most prevalent. So in the summertime, that area is very hot. You have rising air becomes buoyant over that hot land and rises up, and it's replaced by air flowing in from over the Indian Ocean basin, which is relatively cool. Also warm, but relatively cool. And so you get a monsoon wind that's called the southwest monsoon because it blows from the southwest, and it carries all this moist air in over Southeast Asia, and that generates the rainy season. Whereas in the wintertime, the land cools down quickly, and so the land becomes cold relative to the Indian Ocean basin, the surface waters, and so you get rising moist air over the surface waters over the Indian Ocean basin, and that's filled in by wind from the northeast from over the Indian subcontinent. And so depending on what season you're in, you either get a sea breeze in the summertime or you get a land breeze in the wintertime, but they're continental scale. So there's the same physics that goes on down at Kitty Bitty Wharf, but just on the scale of continents and countries rather than just the regional scale of Kitty Bitty. Those changes in the winds are so strong that it actually reverses the direction of one of the key currents. So in the wintertime, we have the Somali current. Here's the Somali here. The Somali current runs down the northeast coast of Africa from north to south. And then in the summertime, the monsoon winds are so strong that it actually reverses the current and pushes it north. And so the Somali current runs north up the coast. And so this is the only place on Earth where seasonally reversing winds actually reverse the surface current, which takes an incredible amount of energy and forces. And here's just a diagram comparing the sea breeze and the land breeze to the situation in the monsoon. So it's just a larger scale version of the same phenomenon. The monsoon winds also affect productivity because of Ekman transport. So if we look in the summertime, rainy season, this sense of wind is going to make Ekman transport to the right, which is going to push water offshore. So we get Ekman upwelling here and lots of productivity. When the wind's reverse direction, the Ekman transport goes onshore, we get Ekman downwelling, and we have very little productivity there. In the Pacific Ocean, the number one thing we talked about was El Nino and La Nina. So these are some of the dominant modes, most important forms of climate variability on Earth. And essentially it's a phenomenon involving the warming of the equatorial Pacific. So this is a diagram that shows what's called the normal conditions. So this would be neither El Nino nor La Nina, it's just what happens typically when we're not in one of those phases. And the structure of the Pacific Ocean circulation is kind of complicated, but I'll run through it quickly. So there's a climatological high pressure on the eastern side of the basin and a low pressure on the western side of the basin. High pressure is associated with descending air and clear skies, and we have sinking air here. The green lines here are an atmospheric circulation called the Walker cell. The low pressure is associated with rising air, cloudy skies, just like there was low pressure in that bomb cyclone, rising air and cloudiness. So you have rising air here, and it's connected aloft in this structure called the Walker circulation. And then between the high and the low, we essentially have the trade winds, which are blowing from east to west. And so what that circulation does is, okay, I'll actually step back for 1 minute. So these winds associated with this high pressure system, they drive coastal upwelling here. So there's a circulation around this high, and it drives coastal upwelling very near Peru here. And it causes the cold waters that are below the thermocline, it bends that thermocline up. So because we're having upwelling here, you're bringing up cold water from below, and that sort of cools the surface waters in the eastern Pacific. Whereas on the western side, there's no such upwelling happening, and so our thermocline is deeper, and our warm surface waters are kind of protected from the cold waters, which are deeper below. So we generally have a cold eastern Pacific, relatively cold, and a warmer western Pacific. And then when you take that and combine it with this Walker circulation, what the Walker circulation does is it drags some of this cold water from the cold pool out into the center, where it's called the cold tongue, because it sort of sticks out like this tongue. And it sort of crams the warm water on the western side in towards the western edge of the basin, and then that's called the warm pool. And so this is sort of the basic setup. We've got the Walker circulation, we've got the high and the low, and then we have shallow thermocline on the eastern side, deeper thermocline on the western side, and then a cold tongue and a warm pool. And so that's the normal conditions. And what happens in El Nino is just you kind of imagine what would happen to normal conditions if you just deleted this Walker cell or if you spun it the other way. And so what happens there is this is normal conditions up here. This is the same diagram as before, but now this is El Nino conditions where the Walker circulation has reversed. And so now the high and low have switched places. We have a flow from west to east along the surface. Walker circulation has reversed, and that now drags that warm water from the warm pool out into the central Pacific. And so this is the main phenomenon that happens when you have El Nino, is that the central equatorial Pacific warms a tremendous amount, 2, 3, 4 degrees Celsius, which when you look at the amount of energy that's involved with that warming, it's a very large amount of energy, as you looked at on the assignment. Another thing that happens is that because this high pressure here is gone, this upwelling stops, and so this thermocline sinks down. You're not bringing nutrients up to the surface anymore, and so the fisheries in this area are affected, and that's a very well-known economic effect. La Nina is the opposite. So La Nina, you take normal conditions and you amplify them. So rather than break down the Walker cell, you make it even stronger. So you push more cold water from the eastern part into the central part, and during La Nina conditions, you cool down the central. So during El Nino, it's a central equatorial Pacific strong warming, and then during La Nina, it's a cooling, so it's kind of the opposite. We quantify El Ninos using this multivariate ENSO index. ENSO stands for El Nino Southern Oscillation. The key things to know here are just that El Ninos happen sort of irregularly. They're not a periodic thing that happens like every 5 years like clockwork. It kind of is irregular. We say we have a strong El Nino warm phase between 2 and 10 years. It's a pretty random number. Very irregular. Generally, an El Nino lasts for about a year or a year and a half, and La Ninas are similar. So they're sort of so just sort of having an idea of this plot that it's erratic, but there's a time scale associated with it. El Ninos generally last a year or a year and a half, and they happen in some irregular interval, generally between 2 and 10 years. El Nino, because it warms such a massive swath of the Pacific Ocean, that affects the atmosphere and affects global weather patterns. So this is sort of very much a cartoon diagram, but all these little dots are places where some kind of statistical change in the weather has been observed correlated with El Nino. And so you can have droughts, you can have impacts on ecosystems, coral reefs, flooding, all that stuff. And so the point is that all over the world, at places that are far from the equatorial Pacific, so for example, India or eastern South America, you have global weather and climate impacts. Because that's so important, we have some observing programs that we've developed starting back in the 80s. There was a really big El Nino in 1982. That spurred a lot of interest. And so there's one called TOGA, which is the Tropical Ocean Global Atmosphere Program. And then the more modern sort of continuation of that is called TOW, Tropical Atmosphere and Ocean. And this is just lots of instrumentation, moorings and buoys and things like that are measuring surface temperatures and trying to assess, is an El Nino happening? How is it likely to evolve? Are we going to switch to La Nina? All those types of things. And those are very, very important because, again, El Nino affects things like hurricane frequency, hurricane paths, all those sorts of things. El Nino is still very much a puzzle. It's not fully understood. It's so complicated and involves so many factors that there are a lot of ideas, and a lot of those ideas, it's not that we don't know anything, we know a lot, but we don't have like one consistent theory that everybody agrees on. And so some ideas involve propagation of equatorial waves back and forth, and that sort of question is trying to answer, that model is trying to answer the question of why do El Ninos occur, every few years, like what causes that time scale? And this argument says it's a wave propagation time, but details of that aren't important. Okay, so then we start to look at the thermohaline circulation. So most of the currents that we looked at, for example, the gyre circulations, Somali current, et cetera, Gulf Stream, those are surface currents. But there's also lots of currents that are below the surface, and we call those thermohaline because thermo is heat, haline is salt, and those currents are driven by density differences. So differences in density are differences in the weight of the water that causes pressure differences, and those pressure forces can drive flow. And so the general idea to think about the thermohaline circulation is that it sort of is driven by the high latitude surface ocean. So up in the polar regions, you get very, very cold water that becomes very dense and it sinks. And then somehow it comes up later. There's various mechanisms for that, and that's called the thermohaline circulation. This diagram is called a TS diagram, and this is how we characterize water masses like the water masses that drive that deep circulation. So the TS diagram has one axis is S, the salinity, the other axis is T, the temperature, and so any water, any sample of water will have a particular temperature, a particular salinity, and so it'll plot as a point on this diagram. And a water mass is a region that has similar TS properties. And so because they have similar properties, not necessarily identical, like the temperature might vary by fractions of a degree or whatever, but they plot as a cluster of points or a region on this diagram. And so for example, NADW here, we'll come back to that, that stands for North Atlantic Deep Water, and then that has a typical salinity of about 35 parts per thousand and a temperature of about 4 degrees. And so you may be asked to interpret or plot a point on this diagram, and generally understanding what the axes are is important. The other feature of the diagram is these curved lines. The curved lines show the density. So in general, we know the density is a function of temperature and pressure. So what these lines say is that if you're at the temperature, salinity 35.5, and you're at the temperature of 5 degrees, then you're on this particular line, so it means your density is 1.0280 grams per centimeter cubed. And you might want to note the conversion between grams per centimeter cubed and kilograms per meter cubed is a factor of 1,000. So this would be 1,028 kilograms per meter cubed. So you just multiply by 1,000 to convert between units. Okay. So as we mentioned, so what happens is in the northern hemisphere, so now this is a diagram showing the sort of a slice through the thermohaline circulation. The weird thing is that north is at the left-hand side, and south, which is Antarctica, is on the right-hand side. So in the polar North Atlantic, you have really, really cold surface waters. This happens in the Labrador Sea especially, and the Nordic seas. It gets cold and then sinks down. The same thing happens near Antarctica. You get very, very cold water, and actually it sinks all the way to the bottom. The Antarctic water that sinks down is called Antarctic bottom water. That's the coldest, densest water in the global ocean. And so that fills up the bottom layer, and just sinks to the bottom and sits there. And so we have Antarctic bottom water at the bottom, and then the cold water formed in the North Atlantic deep water is not quite as dense, and so it settles in sort of a tongue in the middle. And also we can point out that The mixed layer and thermocline tend to happen in the more subtropical regions. So when you get up to the cold poles, we have all this deep convection happening, and we don't really have those well-defined layers of the surface mixed layer and the thermocline that we have in the mid-latitudes in the equatorial region. Okay, so this water sinks down, and it's going to come up somehow, and a key thing is that it takes a long time for it to come up, so these are very slow-moving circulations. We're talking timescales of hundreds or thousands of years for this water that sinks to the bottom to eventually come back to the surface. The North Atlantic deep water forms in 3 key locations, the Labrador Sea, the Nordic Seas, and then also the Mediterranean Sea. The water from the Mediterranean Sea is not as cold, but it's very, very salty. And then all those 3 sources, they kind of mix and intermingle in the North Atlantic, and we call that whole collection North Atlantic deep water. So if we're sinking volume down from the surface, it has to come back somehow, otherwise the ocean would just get more and more compact over time, and the density would increase or something like that. So the water has to somehow get recycled to the surface. There are 2 main ways that happens. This is a complicated diagram that just is meant to show that there's complicated sort of turbulent flow and waves and stuff happening in the interior. And those waves, just like surface waves, can break. And when they break, they cause mixing. And so, for example, here we have, this is an example of the mid-ocean ridge. It's a schematic. We have tides. We're going to cover tides next, but tides flow back and forth over this, generate waves. Those waves can break and cause stirring. And you can imagine if you sink this water to the bottom, and if you just took a spoon and kind of stirred the ocean, it would gradually stir some of that dense water back up to the surface very gradually. And so that's the idea of this mechanism. And another mechanism is called pumping. So in the Southern Ocean, we have winds and Ekman transport. And the Ekman transport kind of spreads out the surface water, and we need water to come from below. And that's shown on this diagram here. These slanted lines here are showing that, so water circulation basically follows these lines. So this is North Atlantic deep water sinking here, flowing south through the center of the basin, and then upwells abruptly in the Southern Ocean. This is in the Antarctic circumpolar current. So there's 2 mechanisms. There's sort of diffusive mixing upwelling that happens that's associated with this mid-ocean ridges and flows and tides over topography and things. And then there's abrupt upwelling in the Southern Ocean. We measure the thermohaline circulation using this array called OSNAP and other related ocean observing projects. This is just a whole bunch of instrumentation that they basically put along a certain line, and they measure a certain line of latitude in the ocean, and they measure how much flow in the surface layer and the deep layer is crossing this line, and they assess our sort of overturning AMOC thermohaline circulation. When we look at that data, it shows some pretty amazing stuff. Basically, the AMOC fluctuates really, really wildly. So you can have changes on the order of 100% or more than 100% from year to year. In general, it has some average value, some average strength, but it fluctuates quite a bit. And this prompted people to think, if it's very, very sort of erratic and changes a lot, could it undergo even more dramatic changes? And so people looked at this with climate models. And so this is an example of a very old climate model from 1995. Where they asked the question, could the AMOC be sensitive to meltwater from Greenland? So the idea is that the way that the AMOC is driven, at least partially, is you get cold water in the North Atlantic that sinks down. And to have that sink, you want it to be cold and salty, are the 2 things that make something heavy. So if you make it fresher, it's less likely to sink. So the question is, you have Greenland, we're doing climate change, we're melting ice on Greenland. That melted ice flows out as fresh water into the North Atlantic here. If you freshen the surface, that makes it less dense, so maybe it will sink less, and maybe that'll affect the strength of the AMOC. So they looked at this in a very, very crude climate model, but it was the best we had at the time. What they found was very interesting results that sort of revolutionized climate science and changed it forever. Which was that, so now this diagram is showing the experiment they did with the model. So the x-axis is how much melting is happening, so how much fresh water is being produced by Greenland. And the y-axis is how strong is the AMOC. And what they found is, as they started to increase the amount of fresh water, the AMOC got gradually weaker and weaker, because we're freshening the water and sinking less. You get a less strong driving, and so the AMOC gradually weakens. But there were certain things that they called tipping points, where if you increase just a little bit, so if you're at this particular place, so the AMOC has a certain strength, if you increase just a little bit, there's a vertical wall here, you fall off, and the AMOC abruptly collapses by about a factor of 50%. And then if you keep increasing the fresh water, it collapses all the way to 0. And so this shows that there can be states of the climate system, at least in models, where small changes in warming and melting can lead to very, very significant changes in the AMOC, which would have lots of ramifications for the climate. And then the even probably more surprising and startling thing is when they then take that melting away, the model does not go back up the same slope, and it does not return to its previous point. It stays weak or at zero until you actually start adding salt water to sort of kick-start it again, and it abruptly jumps from no circulation all the way back up to a healthy circulation. So not only are there tipping points, which are called bifurcations, there's also this phenomenon called hysteresis, which is the same thing as irreversibility. It's an open question whether or not that happens in the real climate. Okay, so we talked about waves. In the wave course, we talked about various examples of where waves happen in the climate system. This is an example of surface ocean waves. We also said they can happen in the atmosphere, so these are wave fronts and cloud patterns, and that they can happen between different layers of water. So we have waves at the surface, that's the atmosphere-ocean interface. Waves can happen between layers of the atmosphere, like say troposphere, stratosphere, and they can also happen between layers of water. So if we have some lighter water, maybe it's fresher or maybe it's warmer at the surface, and you have colder or saltier water beneath that, we can have waves undulating on that interface. And so these could happen, for example, in the picnic line. And the things that we need for waves are basically two effects: some kind of disturbing force, some force to get the wave going, and we need something that brings the ocean back to its previous state if it gets disturbed. And that's called a restoring force. And for all these waves, that's provided by gravity, which is why we call them surface gravity waves. These waves fit into different categories of waves in general. So we talked about a few different kinds of waves. Longitudinal waves are like sound waves where the motion is back and forth. In terms of the particles move back and forth along the direction of propagation of the wave. Transverse waves are like waves on a guitar string, where the motion of the particles is sideways, whereas the wave propagates left and right here, so the motion of the particles and the motion of the wave are orthogonal. Then the type of waves that are most important for us are called orbital waves, and so those are waves where the particles undergo these circular motions, or they can be ellipses, depending on if you're near the sea floor or not. And so ocean waves have this property that the particles do not move either back and forth or up and down. They do both. They move in these circular patterns. And we looked at this diagram, which shows how particles in a surface wave field move. And they execute these circles. And there's two observations. One thing is that the circles get smaller as you go down, so the waves are sort of surface intensified. So most of the energy is at the surface, and the motion gets very, very slight as you go down to deep depths. The other thing is that these circles don't close, and so as you go through these circles, it kind of becomes a spiral or loop-to-loop pattern that gradually drifts to the right in the direction of the propagation of the wave, and that's called Stokes drift. Okay, wave characteristics. So waves have lots of different characteristics, so this is sort of a review. The crest and the trough. The wave height is the difference from the crest to the trough. The wave length is the distance between two successive crests or troughs. One important thing to remember is the wave base. So the wave base is a vertical level below which there's very little wave motion. So we said the waves are surface intensified, but once you get to a certain depth, there's hardly any motion at all. And that wave base is equal to half the wavelength. That just comes from the theory of waves. In time, we also have important properties. The period is the time between two successive crests, and the frequency is 1 over the period rather. And the wave speed, the fundamental definition of wave speed is the wavelength divided by the wave period. We usually use L, or also lambda can be used for wavelength, and T is pretty much universally used for the wave period. So if we look at a wave, imagine this could be undulations of the sea surface, and it's propagating to the right, the speed at which this propagates is equal to the wavelength divided by the period. One way we represent wave data is by asking how much energy is in waves with certain properties. So what we do is we take our full field of motion and we sort of decompose it, and we say how much energy, so the y-axis is energy, and the x-axis is frequency. So how much energy is in our flow that's contained in waves with certain frequencies. This is in cycles per hour, but you can think of this as hertz or per second or any other units of frequency. The key thing is we get some complicated wiggly distributions, hard to make sense of, but the key thing is that there are peaks in this, that I'm looking for the peaks is the main thing. So if you're looking at, this is called a power spectrum diagram, and whenever you look at a power spectrum, the only thing people really look for are the peaks. And so in this case here, there's a peak here labeled M2, that's a tidal peak. So we're going to study tides next in the course. So there's a very regular oscillation that has either a 12-hour or a 24-hour frequency, and that shows up as a big spike in the power spectrum. This one here is labeled F. F has to do with the rotation of the Earth, so that's also a time scale. There's oscillations that happen in the climate system that are associated with the rotation rate, and so there's a big peak there also at F. Okay, breaking waves. So we all know that waves break. We've seen it happen on the beach. So we can actually predict when that's going to happen, and it has to do with this parameter called the steepness. The wave steepness is defined as the height, which again is the crest to trough distance, different from the amplitude, so it's twice the amplitude, divided by the wavelength. And if the height divided by the length gets bigger than 1/7, so if the height is large enough that that ratio is bigger than 1/7, the waves tend to break. And if it's lower than that, then the waves are stable. They're not likely to break. We separated our waves into two simple categories. Deep water waves and shallow water waves, and these had to do with the relationship between the sea floor and the wave base. So the wave base, again, is half the wavelength, very little movement below that line. If the wave base sits above the sea floor, which means that the water depth is greater than L/2, they're called deep water waves. And deep water waves have this very interesting property that the speed of the wave here, the speed's on the y-axis, wavelength is on the x-axis. The speed depends on the wavelength, and it gets faster as the wavelength gets longer. So longer waves, they travel faster, and that's a property of deep water waves. Shallow water waves happen when they feel the seafloor. So when the wave base actually kind of makes contact with the seafloor, and the mathematical criterion for this is that the depth is less than 1/20th of the wavelength. So the waves feel the seafloor strongly, and these orbital circular motions of the parcels, when you get near the seafloor, those circles can't penetrate the bottom, and so you just end up with sliding motion back and forth. And for shallow water waves, the physics is actually much simpler than deep water waves, because the speed is just constant. All different wavelengths have the same speed. It doesn't depend on what kind of wave you have. As long as they're shallow water waves, the speed is the square root of gravity times distance. Sorry, gravity times the water depth, where g is just 9.8. And so any formulas like this you'll be given the dispersion relation, given the formulas for the different wave speeds and things like that, but you may have to do algebra to convert between the different formulas. Okay. The fundamental dispersion relation is this one here. So if you're asked what is the dispersion relation, it's this equation. The square of the angular frequency, omega is 2 pi over period, is equal to g, that's gravity, times k, that's 2 pi over the wavelength, times the hyperbolic tangent of the product of k times d. This formula in its full form, we basically will not use directly. We will use the approximate forms of this that are the speed formulas for the shallow water and deep water waves, but those two speed formulas can be derived by making approximations of this tan h function. And so we did some examples. We used this and we derived that the speed in the deep water case is lambda g over 2 pi. Similarly, the speed in the shallow water case is c equals square root of g times d, and these can be gotten directly from omega squared equals gk tan h kd. I will not ask you to do this derivation on the test. Thank you. Yep. Okay. But you can very quickly from that formula get a sense of how fast tsunamis move. Tsunamis are a strange case because they're in the open ocean, 4 kilometers of water, but the wavelengths are so long that they're still shallow water waves. They feel the seafloor very strongly. And so if you just put in the whole depth, the 4,000 meters for the depth of the water here, those tsunamis travel at 200 meters per second, which is extremely fast. So I did a couple of examples here. You should definitely know these examples. If you're given things like the wave period or the wave length, using the deep water speed relations to solve for things like the period or the speed, you should be comfortable with these examples. So I'm not going to go over them again, but just following through these examples and make sure you understand how to use those. Mainly the two formulas are c equals the square root of g times d, and the wave speed equals the square root of lambda g over 2 pi, and then the fundamental formula for the definition of speed is c equals the wavelength divided by the period. And all those formulas will be on the formula sheet, but you should be able to recognize them and sort of know how to combine them and mush them together and things like that. Okay, so we said that the longer the wavelength, the faster the waves travel. That's for the deep water waves, and that's actually observed. So we talked about the SWAT satellite. So this is a satellite that was launched a couple years ago, and it's been making really state-of-the-art ocean observations. It's a surface as an altimeter, so it sends down beams. Those beams reflect and then are detected back again at the satellite, and then based on the travel time, it infers the ocean topography. And SWAT made this observation. They were tracking waves from a storm. What they showed was as you get further away from the storm, so the x-axis distance from the storm, and the y-axis is the wavelength of the waves, that the wavelength increases. And this is fully consistent with the idea that the long waves travel faster, because as you're further away from the storm, you see the waves that ran the fastest to get to that point. And so your wavelength increases with distance, and the black line shows that that's not just a qualitative prediction, there's like a specific formula that you could say for how much it should change. We didn't get into that, but the wavelength should get longer. And then the observations are completely consistent with the theory, which just shows that this dispersion relation formula, we observe it from space as well. We talked about how gravity waves are generated by wind. So the first step is we get capillary waves. Capillary waves are different from gravity waves because the restoring force is surface tension. So when these waves are really, really small, like just a few centimeters, capillary effects, surface tension effects are important. But for these big waves that are generated later, wavelengths of meters, heights of meters, surface tension is no longer important. So the trajectory is we started off with capillary waves first. Those waves allow the wind to kind of grip the ocean better. The waves get longer, and then they get larger into gravity waves, and then eventually, if the wave height increases sufficiently such that the steepness gets bigger than 1/7, then the waves are gonna break. The largest waves tend to be places where you have the largest wind. So this is the Southern Ocean, very strong winds down here, and we have lots of wave activity. Also, this is the storm track, so we get lots of low pressures and cyclones and things near Newfoundland. Lots of waves out here too, and also that happens in the North Pacific as well. There's basically three main factors that determine how big a wave field you're going to get, and those are called the wind speeds. That's obviously the faster the wind blows, the more waves. How long the wind has been blowing for, that's the duration, and then fetch. And so fetch is the one that's can be a little bit confusing, and that's just how large an area the wind is blowing over. So in the Southern Ocean, the winds blow basically steadily over the whole planet. So you have a really, really huge fetch, strong wind speed, and high duration. That's why we have very, very strong winds in the Southern Ocean. We talked about group packet propagation. So the key idea here is this is a bit subtle, but the key idea is that there's two speeds associated with a wave. There's the speed at which the individual crests travel, and that's the red dot, and that is a faster speed. And then there's the speed at which a group of waves travel, and that's the speed of the green dots. And the point is that the crests travel faster than the group. So the crests start at the back, and then as the group propagates to the right, the waves actually make their way up through the group. They start at the back, they go to the front, and then they kind of dissipate. And so the waves, they travel in this sort of weird envelope. You can spend a lot of time thinking about this, but basically there's two speeds. There's the speed of the crest and the speed of the groups, and the speed of the crest is twice the group speed. So there's two speeds, phase speed, and then group speed. Waves interfere with each other. So if you have waves that are propagating in from different locations, maybe driven by different storms, if they propagate into the same location, you just add them up. So the resulting height of the two waves is just the sum of the heights of the previous waves. If you add lots and lots of waves together, you can get a random wave field. That random wave field has a tail, so like you have some statistical average, and then you have like 1 sigma, 2 sigma, like how many standard deviations away from the center are you? And then out on the tail, you can get very, very large waves, and those are called rogue waves. Near the shore, what happens is when waves approach the beach, they go from being deep water waves to shallow water waves, because the water gets so shallow, you start out as deep and then transitional, and then you get shallow. When you're in the shallow water regime, the speed goes like the square root of the depth. So as the water depth gets smaller, the speed gets slower, and the waves kind of pile up. And so what happens is the waves kind of start bumping into each other, the wavelength decreases, the energy accumulates, so the energy goes up, the height goes up, and then the waves tend to break. And so that's the process as waves hit the shore. That leads to breaking waves. The breakers are categorized into 3 categories based on the slope of the seafloor. We have spilling breakers is the shallowest, plunging breakers are in between, and surging breakers are the steepest. So just maybe knowing the ordering is important, and knowing that there's different kinds and that the physics of wave breaking depend on the slope. I'm not expecting you to remember these specific thresholds or anything. One of the last topics I'm just going to go a couple minutes over here. Wave refraction. So we said that as the waves near the beach, we all know when you sit on the beach, the waves come in parallel, so that the crests are basically lined up with the beach like that, as opposed to propagating this way. And there's dynamics to that. And if you just sort of ask, if we had waves that are initially propagating in at some angle, we know that different parts of this wave crest will travel at different speeds because the speed depends on the depth of the water. And we generally have shallow going to 0 depth here and deeper depth out here. We did an analysis and showed that those wave crests, they rotate. And so understanding this physical argument, that could be something that you're asked. And that causes waves to accumulate on headlands and spread out in bays, and this has consequences for sediment transport. Generally, over time, it causes erosion of the headlands and deposition of sediment in bays. Then our last topic was tsunamis. So tsunamis are very, very large-scale surface waves that are essentially shallow water waves. And the reason they're shallow water waves is because they're incredibly large-scale, hundreds of kilometers of wavelength. So even though they're in 4 kilometers of water, they're still treated as shallow water waves, but they have the physics of shallow water waves, and they come from underwater earthquakes primarily. And you can imagine this kind of situation where the seafloor, there's a fault, and there's some slip along the fault, so the seafloor just drops. That causes the surface to drop, and that creates a wave that has an incredible amount of energy, equivalent to hundreds of thousands of nuclear explosions. These waves, these large tsunami waves, they tend to happen in the Pacific Ocean mostly, because that's where the Pacific Ring of Fire is. So there's lots of plate activity happening all around the edge of the Pacific Ocean, and so that generates lots of seismic activity that can cause tsunamis. These things are extremely dangerous, obviously, and so we've developed some techniques to try to warn people and prevent loss of life and damage. These are called tsunami watches and tsunami warnings. And the type of instrumentation that we use is basically we have different buoys and pieces of instrumentation that are more to the bottom, and we also have deep ocean pressure sensors, because actually in the open ocean it's often hard to see these waves, because actually they only get big when they're near the shore, and that energy starts to pile up. So in the open ocean they're not so big, so it's kind of hard to see them, for example, visually, or it's maybe hard to see them with radar, but we can sense them by deep ocean pressure fluctuations. And so there are a couple of new institutions, the Pacific Tsunami Warning Center and DART, with the Deep Ocean Assessment and Reporting, which are relatively new observational systems that have been put in place mostly since the 2004 Indian Ocean tsunami, which was very, very devastating, to try and prevent future disasters related to tsunamis. Okay, so that's the last, so tsunamis are the last topic, so I will stop there. I will try to post a list of diagrams that are good to know, and again, you know, anything that's covered in the slides can be on there, but I'll post a list, which is a very, very good starting point. Okay, well, have a good weekend, everybody. Feel free to let me know if you have any questions, and I will try to post the solutions for the assignment probably late tonight or early tomorrow, so you can have it for your recovery. Okay, bye. See you every Monday, and try to remember to bring a calculator.